And we're set. So any questions from the last time that we were together with regard to what we're doing with Laplace transforms? Not why we're doing it, with what we're doing with Laplace transforms. So somebody go ahead and take a stab at talking about what is the Laplace transform and what's the idea behind the Laplace transform. Anybody want to take a stab at that?
So we can change from the time domain to the frequency?
Outstanding. That is the crux of what we're doing. Laplace transforms, Laplace time domain to frequency domain. The t in the function tells us that's the time domain going to f of s. Notice we just use a lowercase in the time domain, uppercase in the frequency domain, and then this s here in the frequency domain, that s is a frequency. We talked about it being a frequency the other day. What kind of a frequency? Where do we see that frequency? In what function and where? Tougher question. In what function and where? We've seen it already several times. We saw it in the development of the characteristic equation.
So when we're dealing with natural frequencies?
Okay, that's right, when we deal with natural frequencies. So what kind of a function is that frequency found in? It's weird, I know. Most of us would think, oh, function, frequency, it must be a sinusoid.
Isn't it e to the at? That's
correct, except we're going to call it e to the st, right? It is the e to the at. That is indeed the function that we see it in. So that is called a frequency, and we've lived through the world of math never thinking that an exponential function has to do with a frequency. But the reason it's a frequency is because in general, s is complex, which means it's e to the alpha plus j beta times t. And we know that breaks up into e to the alpha t, e to the j beta t, and we know this is cosine of beta t plus j sine of beta t, and that's where the frequency exists. It's right in there. Okay, excellent. So that's what Laplace is about. So we've been looking at some Laplace transforms. So here we go, testing. Let's go to a new sheet. We don't need to see that one. So let me just pull up a new sheet here. Okay, so for us, let's just put this date up here. We came up with some functional transforms, some Laplace transforms. So I want a table of f of t's and their equivalent f of s's. And this is not a complete table for when we're done, but we looked at some Laplace transforms. Somebody remind me of a Laplace transform of the time domain function and what its Laplace transform is in the frequency domain. Any function.
The delta t, the impulse function.
And its Laplace transform, Jack, is?
1.
That is correct. And then we said, well, what the heck? Let's do all of the singularity functions. R of t, don't forget R of t is tu of t. And so that is 1 over s squared. So we have those. Then we looked at the cosine of omega t. And we said that Laplace transform is s over s squared plus omega squared. Then we used a property to find the sine of omega t. And we know that is omega over s squared plus omega squared. And then there was another important function. And for the most part, these are the functions that we're going to see. And that last one was e to the minus at, and that Laplace transforms into 1 over s plus a. So we had those. So these were called functional transforms. And there are a few more that we'll want in this table, but there are not too many more. So these are Laplace transforms, and we're going to want to know these by recognition. When I see 1 over s squared, I don't want to have to figure out what to do with that. I want to know, oh, in the time domain, that's tu of t. So we want to know them by recognition. A lookup table, yes, but we're going to see some of them so often, like this one, you should know that, you should know that, you should definitely know that. You might have to refer to a table for these three, might have to refer to a table, but the others you should know. So we did that. Then we talked about some transform properties. Transform properties. And how many properties did we get through yesterday? Did we get through 7 of them? Yesterday means on Tuesday. Did we get through 7 or was it 6 properties?
Yeah, it was 6. We finished with the domain shift.
Okay, so the time domain shift. We looked at these transform properties. I don't want to run through all of them, but probably critically important that we use almost all the time is the following. A times f of t plus b times g of t, and I used capital letters the other day, transforms into a times f of s plus little b times g of s. Okay, so if I'm multiplying the time domain, it multiplies in the frequency domain. If I add in the time domain, it adds in the frequency domain. Subtract, same thing. Multiplication, no way. In fact, one of the reasons that we want the Laplace transforms that you're completely unfamiliar with, and I hope we get to it in our course this semester, has to do with the convolution integral. Convolution in the time domain is multiplication in the frequency domain. And it's not multiplication in the time domain, it's multiplication in the frequency domain. We wish it was, but it is not. In fact, multiplication in the time domain is convolution in the frequency domain. And if I believe that you've got the appropriate knowledge of where we're at right now, I don't think any one of you knows what convolution is. So we'll figure out what that is later on. Okay, so we talked about the shifting in the time domain. Let's do property number 7, which would be shifting in the frequency domain. So you can look at this as shifting in the frequency domain, but oftentimes when we look at properties, we always want to know what the property is with regard to the time domain. So if we're looking at this from the time domain, it's multiplication by an exponential in the time domain. That's what it is in the time domain. How do I know it's the time domain? See the T right there? That's how we know it's the time domain. So here's the statement. If f of t has a Laplace transform, and if its Laplace transform is f of s, then the Laplace transform of e to the minus at times f of t is equal to f of s plus a. Just want to remind you, over here I have a negative a, and that transforms over here into a shift of plus a. So the shift f of s plus a shifts to the left or the right. When I take the function f of s, assuming I could plot the function, if I plot the function f of s on the s-axis, does that shift to the left or to the right? F of s plus a, shift to the left, shift to the right.
Left.
Good, it shifts to the left. So this is a shift to the left when we multiply by the e to the minus at. Anybody know the reason why we can't plot these functions, f of s? Anybody have any idea why we can't plot the functions?
Because it's not a time domain function.
No, that's not why. That's a good thought. But it can be, you know, we plot lots of functions in the frequency domain, but we don't plot functions that are functions of s, and here's why. S is alpha plus j omega. So to plot that, I literally would need 2 axes to do that. So I would need the alpha axis, that would be my alpha, my real axis, and then the omega axis here. And so when you start plotting things. You have to do it for every value of alpha and every value of omega, and you can't do that on one plot, unfortunately. So it becomes challenging to do that. So we don't plot these functions at all. We just write them in the frequency domain. Here's the proof. It's really easy. Laplace transform of e to the minus at f of t. By definition, the integral from 0 to infinity of everything inside of here, e to the minus at f of t, multiplied by e to the minus st, and then integrate away the time. Integrate away the time to get a function that is a function of s. E to the minus s plus a t dt. Okay, and I thought we had done this one yesterday, but I could be wrong. So if we didn't, we're doing it. If we did, we're doing it again. But if we didn't, here it is for the first time. So looking at this, remember when we talk about f of s, recall f of s equals the integral minus 0 to infinity f of t e to the minus s t dt. If I change this s to anything, then the change comes over here and over here. Well, up here, I made the change right there. So what should go over on this side? This is equal to what? I don't have an s up here. What do I have up there?
F of s plus a.
That is correct. F of s plus a. That was a pretty simple proof. The proofs are, I like them because they're mathematical in nature, and I like mathematics. To most of us, the proofs are, well, whatever. How do I use the result? That's the question. How do we use the result? So here's an example of using the result. Are you ready? Another Laplace transform pair that we're going to want to know. So let's find the Laplace transform of, and I'm just going to make it general right now, e to the minus at times the cosine of omega t. Well, let's recall that cosine omega t transforms into s over s squared plus omega squared. So I know the transform of that. So think of that as f of t, the time domain function. So if I multiply that time domain function by an exponential, which I've done, there it is, I'm multiplying here by that exponential, we know what happens. It just turns into everywhere there's an s in here, everywhere there's an s, just replace s by s plus a. And be very careful when you do it. So therefore, the Laplace transform of e to the minus at cosine omega t transforms into everywhere there's an s, replace it by s plus a. S plus a, s plus a squared plus omega squared. Notice it's not s plus a and then just only the s gets squared. S plus a, the whole s is replaced by a. Is replaced by s plus a. So I'm squaring s, then I have to square the s plus a. So that is another property that we are going to want to remember. We're going to use that one a lot. Let's use it with numbers. E to the minus 3t, cosine of 10t. Laplace transforms into s plus 3, s plus 3 squared plus 10 squared, which is equal to s plus 3 over. If you want to leave it like this, you could leave it like that. If I was leaving it one way, I would leave it like this. The reason I would leave it like that is because we're going to recognize that in our lookup table. If I'm doing the expansion here, I'm going to write it the following way. I'm going to write it equals s plus 3 over s squared plus 6s plus 109. That's the way I'm going to write it. Why? Because it gives me a polynomial in the numerator and a polynomial in the denominator, and we're going to be dealing with polynomial functions. Yeah, let's do another one. What happens if we have e to the 6t cosine of 4t? That Laplace transform is s minus 6. This, remember, is minus a minus 6. So this is e to the minus 6t cosine of 4t. That's what that really is. One of the games you're going to recognize we play in engineering a lot is we have to make sure that what we are looking at as a function is in a form that we recognize. The form that we recognize is e to the minus a t. That's the form that we recognize. So we have to put it in that form. So this is s minus 6 over s minus 6 squared plus 4 squared. And I'll just leave it like that. Obviously, you can expand that into s minus 6 over s squared minus 12s plus 52. You can do that if you want to, but you don't need to. Okay, check out this example. Try to do examples that are enlightening to you. So we know that f of t, which is equal to e to the minus 8t, transforms into, right, f of s, which is equal to 1 over s plus 8. We know that. I want you to consider the following. Let's consider e to the minus 3t, but I want you to think of e to the minus 3t in a different way. How can it be written? E to the 5t times e to the minus 8t. I think everybody knows that. I think also we all know what this Laplace transform is. Somebody tell me what the Laplace transform of e to the minus 3t is.
One over s plus 3.
Thanks, Jack. 1 over s plus 3, indeed. Now I'm gonna develop the same answer using the property function. So we know this Laplace transform, there it is. I'm multiplying by e to the minus 5t. So again, the way I wrote this before, this transforms into 1 over s plus 8. So therefore, e to the 5t times e to the minus 8t, which we all know is this, must transform into 1 over, now replace s by s minus 5 plus 8, son of a gun, equals 1 over s plus 3. Check. Exactly what we knew already. We already knew the result. I'm just going to show you how it works all over. It works in all different worlds. And in many of these times, it works in the world that we know already. Okay. So let's go on to property number 8. Property number 8 is the time scaling property. So we want to scale in the time domain. If f of t, Laplace transforms into f of s, then time scale that. Well, how do I time scale? F of at transforms into 1 over a f of s over a. And this proof is fairly easy, so we'll do this one as well. I do want to put a restriction on this. A must be greater than 0. Anybody tell me why I'm going to restrict A to be greater than 0? A is a constant. A is a real. It's a real constant. It's not complex. It's a real constant. What do you think the restriction of A being real? Why is that important? What happens when A is negative and we have a negative value inside here? What does that do to the function? In words, what does it do to the function? In words, not mathematically. What does it do in words? If A is a negative number, it will flip the function about the y-axis. Why is that a problem? Here's a function. And so if A is negative, it will scale it. So it'll either accordion in or out, but it will flip it around the axis here. So the first thing it'll do with the negative sign is I'll get whatever that looked like, and then over here. So that's the first thing it'll do. And then it will either squeeze it together in this inward direction or in the outward direction, one or the other. Why is it, so why the restriction on A being greater than 0? Why don't I want that to happen?
Because we're working with a one-sided Laplace transform.
Thank you, Connor. If we're working with a one-sided, we're throwing all this away. And if we do a flip, now we're throwing this away, and all of a sudden we get that function, which is completely different. And there would be no relationship. So it's the one-sided Laplace transform. So we're going to restrict A being greater than 0. Later on, we could do the two-sided and some interesting things happen. But right now, we're focusing just on the one-sided. All right, let's take a look at this proof. So the Laplace transform of f of at is equal to the integral from 0 to infinity, f of at, definition of the Laplace transform. I'm going to keep saying this over and over to you. Whatever's in here goes in here. Then I multiply it by e to the minus st, and then I integrate away the time. I integrate from 0 to infinity. All right, let's do a u substitution. Let u be equal to at. So if we do that, t is equal to u over a. Everybody can see that, I'm sure. And du is equal to a dt, or dt is equal to 1 over a du. Okay, so this now is equal to, check the limits. So the limit on t is 0. So the u value is 0 times a. 0 times a is still 0. At the upper limit, t is infinity. Doesn't matter what my value of a is, as long as a is a constant, and it is, that constant times infinity is infinity. So I still have the integral from 0 to infinity. Now, I have f of u, because u is at, so I just substitute in f of u for at, e to the minus s. Now I have to substitute for t, and that substitution is t is equal to u over a. And then I have to substitute for dt, which is 1 over a times du. Okay, we're almost there. Equals 1 over a. That's a constant. I can pull it out of the integral. It has nothing to do with u. Integral from 0 to infinity. F of u is fine. I like that in that form. But here, I'm going to change this. I'm going to change the e part to e to the minus, and then in parentheses, s over a times u du. Now, I didn't do this yesterday, but I'm going to do it today. Those of you who've had me in class before, and we've talked about integrals, I keep talking about that this here is a dummy variable. We've talked about dummy variables all the time. It's just a dummy variable. We can call it whatever we want to. So I want you to see, if I can call it whatever I want to, I can clearly call it t. So everywhere there's a u, change it to a t, and maybe you'll see this better. So this looks like the Laplace transform. I've got a constant multiplier out in front, but it's not the Laplace transform because the Laplace transform would have an S there, but we have an S over A. So then it must be the Laplace transform with S replaced by S over A. And that is not bad at all. That was a fairly reasonable proof. Okay, let's look at an example of this. I'm going to continue to use some goofy examples. Don't ask me why, but I've got this, I have this like for these goofy examples because sometimes they help us understand some interesting things. So I'm going to go to a picture afterwards, but this is what I want to do. I want to find the Laplace transform of u of 10t. U of 10t. So using this property, we know, or we recall, that u of t transforms into 1 over s. So what I have here is I have u of 10t. So u of 10t, my a value is 10. It's the same function, but my a value is 10. So that should transform into 1 over 10 times f of s over a. This with s replaced by s over a times I know you're all pretty good at multiplication, so I'll spare you the agony. Anybody stunned by that result? Anybody recognize anything?
Is it because there's no value of a for u of t, then it's going to still be 1 over s no matter what the multiplier is?
Okay, so, but it tells me when I scale this function, right? I did a time scale, here it is. I did a time scale. So right now, let's look here and here. Same function or different functions? Anybody? Same function or different functions?
They're different, but they have the same behavior.
Outstanding. They are different functions. Here in the frequency domain. Now we haven't focused on this, but first of all, same function or different functions? Frequency domain. Same or different?
Same.
Same. This is what that tells us. Because the function in the frequency domain is the same, the functions in the time domain must be the same. This tells us that u of t is equal to u of 10t. Now I'm going to prove to you that that's true. Let's look at u of 10t. And I'm going to sketch it. So u of 10t, by definition of the unit step function, is 0 when 10t is less than 0, and it's 1 when 10t is greater than 0. Let's work on this, and let's work on this. 10t less than 0. Divide both sides by 10. What's 0 divided by 10?
Infinity.
Not infinity. 0 divided by 10? Don't overthink that one, Jordan. 0 divided by 10.
0.
Yeah, that's 0. So that's the same as t is less than 0. Obviously, I can do the same thing here. Divide both sides by 10. T greater than 0 divided by 10. 0 divided by 10 is the same as t is greater than 0. Well, true or false? That is the definition of the unit step function u of t. And the answer is, that is true. So u of 10t is equal to u of 5t, which is equal to u of 7t, equal to u of pi t, which is equal to u of 8,000 t, which is equal to u of t. They're all the same function. And we have shown that by looking at that function in the frequency domain. So what we didn't talk about in the frequency domain is the Laplace transform. In order for this transform to work for us, the Laplace transform must be 1-to-1. Shown this way, 1-to-1, or written 1-to-1. The Laplace transform's got to be 1-to-1. That means any function in the time domain maps to only one function in the frequency domain. And any other function in the time domain does not map to the same function. That can't happen. Well, it just did for this function. Why did it happen for this function? Because these two functions are the same. They're written a different way, but they are the same function. However, we can show for the one-sided Laplace transform that it is not 1-to-1. The mapping is actually many to one. I can have many functions over here, and they can all map over into the frequency domain to the same one. Whoop, 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 and there. How is that possible? How can 4 different functions map to the same one in the frequency domain? How is that possible? Here's how it's possible. They do the same thing over here, but the 4 of them do 4 different things over here. But they do exactly the same thing over here. They do the same thing on the one side. So the one side of the Laplace transform is 1-to-1, provided all we're looking at is t greater than 0. Provided all we're looking at is t greater than 0. Okay, here's another example. We know f of t, which is equal to r of t, has a Laplace transform, which is 1 over s squared. Let's find, let f of t be equal to, or let's call it g of t, different function. So g of t is equal to r of 10t. Let's do the same thing, r of 10t. All right, let's use the property to find its Laplace transform. So its Laplace transform is so I have, first of all, I have a 1 over 10 out front, and then 1 over s squared, but not s. S is replaced by s over 10 squared. So this is going to cancel with one of these 10s down here. It'll cancel with one of them, but not with both of them, right? So this is equal to 1 over s squared divided by 10, which is equal to 10 over s squared. Which, by the way, is equal to 10 times 1 over s squared. Well, we recognize 10 times 1 over s squared. We recognize in the frequency domain, this is the Laplace transform of what? So if I were going back to the time domain, 1 over s squared is the Laplace transform of what?
R of t.
Excellent, Jack, you're on it. And then this is just the multiplicative factor, correct?
Yeah.
So there it is. So r of 10t that we started with here must be equal to 10r of t. Notice, unlike u of 10t was equal to u of t, we don't have r of 10t is equal to r of t. We don't have that. It's not true. In fact, it's equal to, instead, 10r of t. So that's interesting for you to notice. It's not critically important that you recognize it and understand that. Okay, more on properties. Property number 9, t multiplication. Obviously, if it's t multiplication, it's in what domain?
Time.
Excellent. It's the time domain. So if f of t transforms into f of s, then multiply by t in the time domain, and we saw that before. The Laplace transform of that function is going to be equal to minus, oh, you got to be kidding me, you got to be kidding me, you got to be kidding me, the derivative of f of s. So in the frequency domain, we're going to take a derivative of the frequency domain function with respect to s and get a negative sign out in front as well. All right, I want to show you this proof. It's not difficult, but it is different. So let me tell you what most people would do, which is the wrong approach. It's much more challenging to do this. So most people would look at it this way. So we know the Laplace transform of t times f of t is equal to the integral 0 to infinity tf of t e to the minus st dt. And then start to work on this side, try to look at use substitutions, integration by parts, et cetera, et cetera, et cetera. And I promise you that that's not trivially easy to solve that problem. So I'm gonna show you an alternate way to prove this. I'd love to tell you I was the one who came up with this proof, but I'm sure you'll appreciate it. So instead of this, so this is a difficult approach. So instead, let's consider this. Okay, so what I want to look at is I want to look at minus dds of f of s. So rather than looking at the left-hand side, which we're used to, and then writing down the Laplace transform, what I'm going to do is I'm going to look at the left-hand side over here, and I'm going to see if, when we're done with our work, it looks like this integral right here, because we know that this integral is the Laplace transform of that side. Everybody understand that? Agree with that? So here it goes. This is equal to negative dds of f of s. F of s is the integral 0 to infinity f of t e to the minus st dt. And I don't want to get into great detail about what an integral really is and what this dt is really a differential element. I don't want to scare the daylights out of people. But what I do want you to recognize is that everything in this integral, this just says take a sum. So this is a derivative of sum. So I can bring the derivative inside of that. So I think you all agree with that. I'm going to leave the negative sign outside, but I'm going to bring the derivative inside the summation. And so it's dds of, now I've got of all of this, f of t e to the minus st, and it's really the dt inside of here. It really is. But dt, we know, with respect to s, is a constant. So I'll leave it on the outside. Okay, so the dt, it's a differential amount of t, is really inside that derivative, but it is constant with respect to the derivative with regard to s. What else inside of that bracket is constant with respect to s? What else inside of here is not a function of s?
f of t.
Good. I'm going to pull it out. And now I'm left with this very simple derivative, which all of us like, the derivative of e to the minus st. And what is the derivative of e to the minus st? Is it minus s e to the minus st? Do you agree with that?
Yeah.
I tricked you. The derivative is with respect to s. Okay, it's not with respect to t. So I want you to look at it this way now. The derivative is with respect to s. So what is the constant that multiplies s in the exponent?
It'll be negative t.
It is. So the negative t comes out in front this time. Weird. Times e to the minus st dt. I have one more thing to do, and then we're home free. What is the one more thing? Anybody? Anybody see it?
You can pull the negative out.
That is correct. Pull the negative out. Those two negatives cancel. It's the integral from 0 to infinity. I'm just going to rewrite this. Here's the t. I'm going to rewrite it and put out in front here. T f of t. Notice I'm not pulling it out of the integral. I can't. E to the minus st dt. And that is what we said right up here. That is the Laplace transform of t f of t. So we have proven that this is equal to the Laplace transform of t f of t. So when we have a t multiplication, of a function, what happens is, as long as I know its Laplace transform, I take its derivative of the Laplace transform and a negative sign in front of it. Okay, well, let's do a function. Let's do a really important function. So we know e to the minus at transforms into 1 over s plus a. I'm going to write it this way, and we generally don't like this, but I like it right now. That is s plus a to the minus 1 power. It's always nice when you're doing derivatives to see it that way. Otherwise, we go into the quotient rule. All right, that means then t times e to the minus at is going to have a Laplace transform, which is equal to negative the derivative of s plus a to the minus 1 power. That's minus 1, s plus a to the minus 2 times the derivative of the inner. What's the derivative of the inner with respect to s?
0.
The derivative of a is 0, but I have the derivative of s plus the derivative of a. What's the derivative of s with respect to s?
1.
Good. dds of s is equal to 1. So all of this is equal to minus 1 minus 1 s plus a to the minus 2 power. Okay, and I dropped this. Let me bring that down here. Excuse me for dropping that. Equals minus, and now this minus with that minus makes it a plus. So now let's write it in the form that we want it. So that means t e to the minus at transforms into 1 over s plus a squared. Do you remember that t multiplier that we had before? Long time ago, the t multiplier, when we had, for example, when we had the characteristic equation had repeated roots. So like we had, if I had s squared plus 4s plus 4 equals 0, s plus 2 squared equals 0, s1 and s2 are both equal to the same number. They're both minus 2, not minus 1. They're both minus 2. Therefore, the homogeneous response was, whatever it is, x homogeneous was equal to, there was a k1 e to the minus 2t, and then there was a k2 t e to the minus 2t. That t is because of that right there. That's what happens. So anytime we have a t multiplier, we have an example of something interesting going on down here in that denominator that's taking place with regard to an exponential. Okay, because this exponential is so important, let's, just for the heck of it, let's see what happens if I do this. T squared e to the minus at. Well, don't forget, that's t times t e to the minus at. And we know the Laplace transform of this. So this is t times this one in the time domain. So over here, it's minus dds, and it's the derivative of this Laplace transform, but I have that Laplace transform. It is, and I'm going to go back to this form, s plus a to the minus 2 power. Come on. All right, so that's equal to negative a minus 2 s plus a to the minus 3 power, which is equal to negative a negative 2, which is a positive 2, s plus a to the 3rd power. We could play that game over and over and over again. So we can continue to look at multiples of t to the 1st, t to the 2nd, t to the 3rd. So let's call this t to the n multiplication. So this property, multiply, spelled properly here today. Multiplication. And that just says, well, what happens if I multiply times t to the 4th, or t to the 7th power, t to the 10th power, t to the 15th power? What happens in the frequency domain? And here's what happens. And you can see this based on the example that we just did. I'm sure you can extend it. So if f of t, Laplace transforms into f of s, t to the n power times f of t, Laplace transforms into minus 1 to the n power. You can see how we keep getting a minus 1 to the n power. And then it's going to be the nth derivative of f of s. So that's our property. We can very easily prove that. If you want me to prove that, I can do that. In fact, let's go ahead and do that. So we'll do it the same way, do it the backwards way. I like to call it the backwards way. Proof. Let's look at minus 1 raised to the n power of the nth derivative of f of s. And that is equal to minus 1 to the n power of the nth derivative with respect of what? Of the integral 0 to infinity of f of t e to the minus st dt. Same exact game. We're going to bring the derivative inside the integral. We can always do that. So that is equal to minus 1 to the n power, integral 0 to infinity, bring the derivative in. What two things are going to come out of the integral? When I bring the, I'm sorry, not out of the integral, out of the derivative. I'm taking the derivative of all of this. What two pieces of that are going to come out of the derivative? Because they're constants with respect to the derivative. What two terms? F of t, dt. They have nothing to do with s. So I'm going to pull right out of the derivative right now. But the e to the minus st has an s in it. So it is a function of s. Well, we know what the first derivative is. So the first derivative is a reminder, the first derivative. I took e to the minus st, I took its first derivative. And we saw that it was minus t e to the minus st. Second derivative, minus t comes down again. So I get a minus t, and then I square it, e to the minus st. Then I take another derivative, another minus t comes down, minus t to the third power, e to the minus st. So the nth derivative is minus t raised to the n power times e to the minus st dt. I'm going to separate this. Recall, minus t, all raised to the nth power, is equal to minus 1 raised to the nth power times t raised to the nth power. So let's substitute that. So this equals minus 1 to the nth power, integral 0 to infinity, f of t, minus 1 to the nth power, t to the nth power, e to the minus st dt. We're almost home free. Constant with respect to the integral. Pull it out front. Now I have minus 1 to the n times minus 1 to the n. The integral 0 to infinity, f of t, t to the n, e to the minus st dt. I'm going to do two things. One, minus 1 to the n times minus 1 to the n is minus 1 to the 2n. Which is equal to minus 1 squared raised to the n power. What's minus 1 squared?
1.
And 1 raised to the nth power. So all of that is equal to 1. So here we go. Then I'm just going to rewrite this, put that over here. This is equal to the integral 0 to infinity. Oh my God, I see it. To the n, f of t, multiplied by e to the minus st dt. Blah, times e to the minus st dt, integrate from 0 to infinity. That is equal to the Laplace transform of t to the n, f of t. QED, done. Beautifully done. Very nice. Okay, that's our proof. We'll come back and we'll look at an example of using that for a function that's going to be particularly important to us. That's going to be the exponential function. So we'll go ahead and we'll take a look at that when we come back from break. So let's take about a 5-minute break here and then come back right at the top of the hour. We're back live. We're ready to roll. Any questions on any of these properties that we've looked at? Because for the most part, I'm going to I'm going to stop with those properties. Those are the important ones that we'll encounter throughout our time in engineering, and the ones in particular that we're going to be recognizing in some of the work that we're doing with Laplace transforms and how we're using Laplace transforms to do circuit analysis. So do we have any questions on any of those properties that we've touched on? So here's what I want to do. I want to take this last property that we looked at, and I want to apply it to a particular function that is important to us. So let's apply property 10 to the exponential function. So when we're talking about a t multiplied exponential, what we want to know is, what is the Laplace transform of t to the n times e to the minus at? And I'm writing it this way, is e to the minus at, not e to the positive at. What is that equal to? And so we know that according to the property, this Laplace transform is equal to minus 1 raised to the n power, the nth derivative with respect to s of what function? Anybody help me fill in the blanks for the derivative of what function? Well, the function that goes in there is the Laplace transform of this, right? I'm multiplying it. Here's my t multiplier. The function I'm multiplying by t is this function. So what's the Laplace transform of that function right there?
1 over s plus a.
And we said, well, if we're going to take derivatives, there's a better way to write it. And the better way to write it is by taking the nth derivative of s plus a raised to the minus 1 power. Okay, what I want to do is I want to start spelling out what these derivatives are for n is equal to 1, n is equal to 2, n is equal to 3, n is equal to 4. So let's start n equals 1. First derivative. So when n equals 1, this Laplace transform is equal to minus 1 raised to the first power, first derivative of s plus a to the minus 1. That is equal to minus 1 to the first, negative 1, times the first derivative. Well, the first derivative is minus 1, s plus a to the minus 2. And I like that form, and I'm going to use that for further derivatives. But let's clean it up first. The minus and the minus is positive. We've seen that already. So it's s plus a to the minus 2. And over here is just as a side note, s plus a to the minus 2 is equal to 1 over s plus a squared. Okay, so that's when n is equal to 1. Now let's go to n is equal to 2. When n is 2, there are two ways to look at it. So we can look at it from this formula and then say it's the second derivative, or we can say it's a single t multiply times the derivative of this function. I think the way that I would rather look at it is probably to kind of see what's going on. It might be to take a look at what happens with regard to the function that we've got written already. So let's see what that's going to be. Well, it's going to be minus 1 and that minus 1 now multiplies the derivative of this function here. So times the derivative of s plus a to the minus 2. And that is equal to minus 1 times minus 2 times s plus a to the minus 3. Let's see, I'm looking at it. I've got another negative sign in here that I don't like. I just did something wrong.
I think it's because it's minus 1 to the n, so it should be minus 1 squared.
Thank you. Minus 1 squared. But Jack, if we look at it this way, t times t e to the minus at. Let's look at this form, right? I have a single t multiplier here. Then that would be minus 1 to the first power, right? There's a single times the derivative of the Laplace transform of this function. Correct?
Yeah, I got you.
That would be, here's my minus 1 to the first power. It's 1 t multiplier. I don't know. It seems like, I think there's supposed to be another negative sign in here. Give me a negative 2. I'm looking at this wrong.
Yeah, I think it would be, so the minus 1 would be to the 2, and then the d by ds would just be to the 1, because obviously we're using the
That's yeah, let's do this. Let's put the 2 there, and then let's do this. Instead of this, let's stick with the original function. This is what I'm going to do. I'm looking at it in a different way. There are 2 ways to look at this. And so let's do this. That's a different way of looking at it, because now that's a different function. So it's minus 1 to the second power times the second derivative. So we already know what the first derivative is. Here's the first derivative, right? Sorry, here's the first derivative. Correct? Minus 1 is the first derivative. Now I have to take a second derivative. So the second derivative, there's the minus 2, and then that's going to give me s plus a to the minus 3. Is that right? I believe that's correct. So now what we have is we have this minus 1 squared. Gosh, darn you. This is what, if you want to know what sucks about being left-handed, it's this right here. Buttons on this device are on the left-hand side, and I put my arm over them, and once I hit it with my hand, it changes everything. Okay. So again, all of these are constants. So when we take the third derivative, n is equal to 3 on the third derivative, what we end up with is minus 1 to the third power. Keep in mind now, there's a minus 1 squared. We showed there's a minus 1 squared in here, and these negative signs inside here contribute to that as well. So then we end up with the third derivative of s plus a to the minus 1 power. So the third derivative is going to be, well, the first derivative brings down a minus 1. The second derivative, we know when we get to the second derivative, we have this function. The third derivative is going to bring down minus 1, minus 2, minus 3, s plus a to the minus 4 power. And you can see how it just keeps changing. So when we look at these in the denominators here, s plus a to the 4th power, s plus a to the 3rd power, s plus a to the 2nd power. So what it does is it just keeps bringing in an extra power. That's what we end up having happen to us on that. Okay, so overall, we get the following in our table, and that table is on page, let me just look this up in your book for you, in chapter 12. So we have two important tables in chapter 12. Just pretend you're looking through the book with me. If you have it next to you, you can see this. And so we've got properties on 458. Oh, it's not in your book. This particular one is not in your book. So this is what I have. And I'm going to double check this for you tomorrow and verify this. So we end up with the Laplace transform of t to the n times e to the minus at is equal to n factorial times 1 over s plus a to the n plus first power. So you can see when we took the third derivative up here, we end up with fourth power down here. And you can see where this factorial is coming from here. The factorial is coming from the fact that every time we take a derivative, minus 1, minus 2, minus 3, the next one is going to bring down to minus 4. And then I can factor out all those negatives, and those negatives should cancel with this. The way I see it, they cancel with that. So this, and I will verify this, so write it down, I'll verify it, because I'm not sure if I made a mistake in my math and whether or not there's a minus 1 to the n power in there, or minus 1 to the n power, n plus 1 power. So that is the overall t to the n. Now, generally what we're looking at is we're looking at n is equal to 1, that's the most common case, and then n is equal to 2. Every once in a while we see n equals 3, but we don't see anything that's larger than that. So we want those inverse Laplace transforms of that particular function. All right, overall, what we can do is we can combine properties for a Laplace transform. Combine properties. So let's do this by example. F of t equals 10 minus 3 squared times e to the minus 2t times u of t minus 3. So let's write that function down. Now, if you look at this, there are a number of things going on. There are a variety of ways to look at this function, so I want to tell you that right up front. There are a variety of ways of looking at this function and solving its Laplace transform. No matter how you do it, if you do it correctly, you will get the right answer. No matter how you do it, if you do it correctly, you'll get the right answer. Here's what I want. I want you to tell me what properties you see built into this. So what are some of the properties? How about the multiplication by a constant? Do you see that one there? So that's part of the linearity property. If I look at t minus 3 times u of t minus 3, that's an interesting function. By the way, u of t minus 3, does anybody know what u of t minus 3 squared is? U of t minus 3, like that function squared? It's both 0 squared and 1 squared. 0 squared when t is less than 0, 1 squared when t is greater than 0. U of t minus 3 and u squared of t minus 3 are both the same thing. So there's linearity. What else is there? There's a time shift. You see the time shift? U of t shifted to U of t minus 3. Over here, here's a time shift. T shifted to t minus 3. That's a time shift. So we have that. So there are time shifting. Multiplication by an exponential. So we have all of those things that are going on in here. So we can apply those properties. So here's what I'm going to do. I'm going to select, and you could select a completely different one. I want to be really clear. You can select a completely different function that is your base function. I'm going to start with my base function. Let g of t equal t u of t. That's my base function. If I do that, what's g of s equal to?
R of t.
G of s. G of s.
One over s squared.
Okay. Now, if I take this function and I multiply it by t. So let's multiply it by t. So t times g of t is equal to, over here first, it's t squared u of t, correct? Using our properties, what would the Laplace transform of t g of t be? Let's call this, let's give these all names. Let's call this one h of t. We'll find out later on, we just don't randomly use h because h is an important function. It's called a system function. So that's a single t multiplier, right? What happens when I do a t multiplication?
You get minus d by ds of f of s.
Beautiful. So in this case, it's going to be that. All right, let's calculate that. That's minus 1 times, this is s to the minus 2, so that's minus 2, s to the minus 3. So h of s equals 2 over s cubed. Beautiful. So we're trying to work our way to this function here. Okay, and this is it takes experience to see this. I know this is pretty sophisticated right now for you. It takes experience to see in which direction that you want to work. So now here's what I'm going to do. I'm going to look at what is h of t minus 3. H of t minus 3. Well, it's what? Is that correct? Everybody like that from the time domain? It's t minus 3 squared times u of t minus 3. And I want you to note what I'm doing. I'm starting to build up this function right here. I still have to do this and I still have to do this, but I'm doing it one step at a time. So it's t minus 3 squared u of t minus 3. That's h of t minus 3. If we call this, let's give it another name. So we have f, g, h. Let's avoid I and j. K of t. So how do we find K of S? What happens with a time shift? Anybody remember? Time shift is a multiplication by an exponential. It's going to be e to the minus 3s all times the Laplace transform of the function that we took, that we shifted. So it's going to be times 2 over s cubed. Okay, that's a number of steps. Let's take this and let's now multiply by e to the minus 2t. So let's form L of t equals e to the minus 2t times k of t. And that's equal to all this times e to the minus 2t. E to the minus 2t times t minus 3 squared times u of t minus 3. Well, just look at it from this perspective. So what's going to happen to the Laplace transform of k of t when I use that multiplying by an exponential in the time domain? What does that cause to have happen? Do you remember? It was a shift in the frequency domain, is that correct? Not sure of that property. Look back at, we did that one today. And that was property number, let's scroll through properties. It's multiplying by t, multiplying by t. Okay. T multiplication, it's still T multiplication, I think. F of AT, the scaling, here it is, this one, this property. Boy, we wrote a lot of notes today. Property, multiply by e to the minus AT, and it causes a shift of a plus a over here. So everywhere there's an S, it's an S plus a. So now if we scroll back down, what's going to happen here is in our Laplace transform, it's going to be everywhere we had an S, it's replaced by S plus 2. This will, let's write, this was L of S equals e to the minus 3 S plus 2 times 2 divided by S plus 2 cubed. Okay, now if we go ahead and again look back at the original function that we were after here, there's only one other thing we have to do, and that's multiply by 10. That's the easiest thing, and so let's just do it. So 10 times e to the minus 2t times t minus 3 squared, u of t minus 3. Laplace transforms into, I'm just going to put a 10 on this side. That's going to give me a 20 in the numerator when I put that in there. And so it's going to give me 20 times e to the minus 3 s plus 2, all divided by s plus 2 cubed. That's the Laplace transform. Now I know that seemed cumbersome, but once you get comfortable doing these kinds of things, it's not so bad at all. But I'll guarantee you the following. There's a guarantee. You would rather do that than try to do the integral on this function up here that I gave you. Where is it? God bless you doing the integral on that. And that is the whole purpose of properties and Laplace transforms the way we look at them. The whole purpose is it is going to save a lot of time when we're doing this, a lot of time. So we can group these things together. And when we group them together, what we can do is just use one property at a time. Let's try another one. Just careful using whichever properties you want to use. Just be careful using them. So f of t is equal to minus 3t e to the minus 5t times the cosine of 4t. There are good choices and there are bad choices. I'm going to choose the cosine as my base function. So let's let f of t equal cosine of 4t. If we do, then we know f of s, the Laplace transform of that, is s over s squared plus 4 squared. And so that is equal to s over s squared plus 16. Okay, so that's the starting point. Then the question is, what do we want to do next? From there, what do we want to do next? I think the best thing to do is get the t multipliers in there. So let's look at t cosine of 4t is going to be equal to, or not equal to, it's going to transform into, it's going to transform into, well, what do? T multiplier. Minus 1 raised to the first power, single t multiplier, the derivative of s over s squared plus 16. I apologize for those who don't like it, but we're going to have to use a quotient rule here. So this is minus 1. Let's leave the minus 1 out in front. Derivative of the top, 1 times the bottom, s squared plus 16, minus the top, s times the derivative of the bottom, 2s, all divided by the bottom squared, s squared plus 16, all squared. That's equal to, leave my minus 1 out here right now. Then I have, in the numerator, I have s squared plus 16 minus 2s squared over s squared plus 16 all squared. In the numerator, one of these is going to cancel with one of those, and then I'm going to take the negative and I'm going to bring it inside. So I'm going to distribute the negative sign in the numerator. That's going to give me s squared plus 16 divided by s squared plus 16. I'm sorry. Numerator, not s squared plus 16, s squared minus 16. I'm bringing the negative sign into the 16 also. All raised to the second power. So that's the Laplace transform of t cosine of 4t. Now let's include this property. So e to the minus 5t times t cosine of 4t Laplace transforms into, what does that do? It causes everywhere there's an s, we change that s to an s plus 5. So it's going to be s plus 5 squared minus 16 over s plus 5 squared plus 16 squared. And then finally, minus 3 minus 3. Done. Laplace transform. And that was beautiful. That was fast. Didn't take a lot of lines. We were able to get that pretty quickly. So those are examples of how these properties come in handy. Now what we want to do is we want to shift our attention to, great, we know how to calculate these Laplace transforms. Now, why do we need them? Well, we need them because we're going to do Laplace transforming of circuits. But if we don't know how to get back from the frequency domain to the time domain, it's of no value. So we must spend some time on the inverse Laplace transform. And so we're going to do our inverse Laplace transforms in a manner that is consistent with the way almost everybody teaches the inverse Laplace transform. So there's an integral you can use, but you have to know how to integrate in the complex plane. You need to take a course in complex analysis and mathematics in order to understand how to do that. And we don't have that under our belt. And so instead, what we're going to do is, because we know in circuit theory, we're going to end up with functions that are rational fractions. We want to know how to do the inverse transforms of rational fractions. So the focus here, the focus is finding the inverse transform of rational fractions. Now, here's a very important note. And I'm not lying to you when I tell you, I remember when I took circuits too, how nobody really made this note to us and didn't really tell us and make it clear. And so on my final exam, I screwed up one problem that I had because I was not aware of this note. So this is an important note. So put some stars around this to make sure you note this. To be able to do this transform, and I should say this inverse transform, the rational fraction must be strictly proper. And I'll define that in a moment, but I want to see if you know what it is. So Jack or Connor, I know you've taken differential equations. You've certainly have covered Laplace transforms there. Did you talk about this in that course?
Yeah, we did inverse Laplace transforms.
Did you talk about, so you did them for because you did partial fraction expansion, is that correct?
Yeah.
Okay, did you talk about making sure that the fraction was strictly proper, otherwise the technique does not work?
I'm not 100% sure. I think
Okay.
I can't remember. We spent a long time on them, so.
Okay, so to be strictly proper means the following. The polynomial in the numerator is of lower order than the polynomial in the denominator. Can't be the same. It must be lower. Must be lower than. I'll give you an example of a rational fraction that is not in strictly proper form. So let's just pretend we're given an f of s and it's equal to 3s cubed plus 2s plus 1 divided by s squared plus s plus 2. You can see the order of the numerator, it's third order, second order. And so this is not strictly proper. So we can't use all partial fraction techniques. So what we have to do is, when we run into this situation, and you will from time to time, when you run into this situation, you must convert this so that you get something that is left over that is strictly proper and something that is the quotient. So here's what we do with this. We perform long division. I'm sure all of you have seen long division, but just to be sure, Always arrange your polynomials in order from highest to lowest powers. 3s cubed. I'm going to put in a 0s squared, include the terms that are missing, plus 2s plus 1. Include the terms that are missing. It's not there. Put them in there. And now I'm going to perform the division. So it's always, what do I need to multiply this by to get the first thing? That's how we start. So we need 3 times s to get that. So that'll give us 3s cubed. And then as I continue along, 3s times s is plus 3s squared. 3s times 2 is plus 6s. And then we're going to subtract. So we perform this the same way we perform longhand division. Those will always disappear, the first ones. And now I have 0s squared minus 3s squared. That's a negative 3s squared. I have 2s minus 6s. That's minus 4s. And I have 1 minus 0, which is plus 1. Okay, and then I'm going to continue this until I cannot divide any further. So I need a negative 3 here. Negative 3 is going to give me minus 3s squared. Then minus 3 times s is going to give me minus 3s. And then minus 3 times 2 gives me a minus 6. And then I subtract. Don't ever forget you're subtracting. Minus 4s minus a minus 3s is negative s. And 1 minus a minus 6 is plus 7. So this, if I did my math correctly, is equal to. So now, all this tells me back here, f of s equals 3s minus 3. We don't throw that away. That's the quotient. And then we have plus this remainder. So the remainder is s. Come on, catch up to me. Thank you. So minus s plus 7 over s squared plus s plus 2. I just want you to look at this fraction now. Is that a strictly proper rational fraction? Is the order of the numerator lower than the order of the denominator? And the answer is yes, and it always will be when you perform your division, your polynomial division. So if you need to, be sure you brush up on your polynomial division. So when we have an f of s that looks like this here, what we have to do is we have to clean it up. These we'll work with separately, and then we do our partial fraction expansion of this. So I'm just going to say that now about ensuring our polynomials are strictly proper. And you're not going to hear me say a lot about that in the future. You just have to do that. Now I want to get into the process of partial fraction expansion. And this is one of the techniques that is covered in Calc 2. Usually in a math course, they do partial fraction expansion very different than the way that we do it as engineers. And if you haven't seen this, the way we do it as engineers, I think that you will agree, as I try to find mine. There it is. I think you'll agree that the way we do it as engineers is a little bit easier than the way mathematicians do it. And so hopefully you'll understand what it is that we're doing, why we do it the way we do it, and understand the difference between what we do and what a mathematician does, and that they're the same thing. So in partial fraction expansion, what we're talking about is expanding a fraction into smaller fractions. That's what we're trying to do. And so when we do that, we know that we like to try to pull the lead coefficient of our denominator out of the denominator. So one thing we like to do is pull the lead coefficient of the denominator. So pull that coefficient out of the denominator. and just include it as a constant in the numerator. Let me give you an example. F of s equals 2s plus 5 divided by 3s squared plus 12s plus 9. Okay, I don't like that 3 there. I always want my lead coefficient to be 1 in the denominator. We don't care about the numerator. So the first thing we would do is factor it out. So there, factor it out. And then we end up with s squared plus 4s plus 3. So we factor that out. And then, that's a 3, by the way, not an s. Factor that out. And then include it in the numerator. Ready? Here it is. Include it in the numerator. 1/3 times 2s plus 5 divided by s squared plus 4s plus 3. Now we're ready to move this into partial fraction expansion form. So that's the first thing that we do. Once we have it that way, then we can start to look at the rest of the denominator and see what the factors of the denominator are. So then factor it. So we want to do that. We want to have it in its factored form. And once it's in its factored form, we know that we can write this as a sum of fractions. And I'm going to show you why we know we can do this. So we know that this is equal to, so I'm going to write it over this side. So 1/3 2s plus 5 divided by s plus 3, s plus 1 is equal to something over s plus 3 plus something over s plus 1. We know that. We put A, B, constants. These are constants. A and B are constants. And the reason we know that is because if I work backwards and I put this all over a common denominator, s plus 3, s plus 1, then I end up with this, A times s plus 1 plus B times s plus 3 in the numerator. And I know that this numerator, since the denominators are the same, must be equal to this numerator. And as long as this numerator has an order that is strictly lower than the order of the denominator, this can always work mathematically, always. So the idea behind doing this partial fraction expansion is get this in its correct form, factor the denominator, and that tells me how to expand it. Well, it should be so trivial. There are several different ways that that denominator can look, and based on how the denominator looks, we have different ways of doing partial fraction expansion. So those expansions are going to look slightly different. So in this particular case, we have what we're going to call case number 1. So in case number 1, we're going to call case number 1 is going to have to do with the roots of the denominator. And so in case number 1, we're going to have only simple real poles. Now a pole is a value of s, a pole, a value of s that causes the denominator to be equal to 0. You can see here the poles for this particular function f of s are -3 and -1. A 0 is a value of s that causes the numerator to be 0 and ultimately causes f of s to be 0. unless we have 0 over 0. Poles are really important because poles are directly related to the natural frequencies of your circuit. Zeros are important because zeros tell us what frequencies can we put into the circuit and it will cause nothing to come out. The circuit will completely filter it out and 0 will come out. That's the idea behind poles and zeros. So case number 1 is when we have simple real poles. This simple term is real and distinct. Real, distinct. They're not repeated. So when we talk about simple, simple means power of 1. In the poles, it means 2 things. Simple, 1. Power of 1. 2. Real number. Even though we say simple real poles, they're real numbers. They're not complex. Okay, so I'm going to give you an example of what that would look like. F of S is equal to 8S plus 19 divided by, and I'm going to factor it for you already, S plus 2, S plus 3. And you'll find a lot of times that you get these factored already for you. So the idea of partial fraction expansion is this is 1 over S plus 2, 1A over S plus 2 plus B over S plus 3. That's the partial fraction expansion. And the question is, what are the values of A and B? And the answer is we can find them real fast. We can find them very quickly. And the way we find those values is going to be pretty different, I think, than what you've seen in your math class. So in the math class, usually what is used to find those values is you do kind of what I showed you back here, is you do this expansion right here. Let me circle that for you so you're staring at it with me. And you're looking at this, and you're comparing the numerator on this side to the numerator on that side, and we can easily solve for A and B. And you can always do that. That is a legitimate legal way to do it. But there are faster and better ways to do it, and we're going to show you the best ways to do it. In some cases, I'll show you multiple ways because you might feel more comfortable with one than the other. There are 3 cases we're going to deal with. We're going to deal with these simple real poles, then we're going to deal with the repeated poles, and what happens there, and then we're going to deal with the complex conjugate poles. And we can tie repeated and complex conjugate together. Once we have those 3 situations, we will be able to do our partial fraction expansion of all functions, and then we will compute the inverse Laplace transform by looking those up in a table and knowing the forms of particular functions. So we'll do that tomorrow. We'll go through those inverse partial fraction expansions tomorrow by stepping through what are the 3 situations. I am not convinced we will get through all 3 situations tomorrow because I'm going to spend particular time going through some examples so that you can get this done and understand it clearly. Any questions before we part ways for the day today? Okay, hearing none, I will see you all tomorrow. Stay safe. Be careful of getting close to too many people who are around. I know that, again, there's a lot of people who think that this whole thing is kind of winding its way down. It is not winding its way down. Please be smart. I'll see all of you tomorrow, and I'll lecture tomorrow. Take care.